Now in this session we'll talk about performance criteria. That means how effective stop and wait protocol is and how good your go backend and SR protocols. How to find out who is good and who is bad. How much good, how much bad. For that we need some metrics, right? So we are going to talk about that metrics. Let's start with stop and wait protocol. Now if there is no stop and wait protocol and see the scenario, we are having, let's say, two computers or two transmitting units, and this A is sending the data to B, right? For that, this transmitter of A continuously can send the data, right? Now 100% this link can be utilized if really A wants, right? If A doesn't want to send, otherwise if A doesn't have any data, then nothing to talk about, right? But if A has infinite amount of data to send, then no one is stopping that A, then 100% with utilization your sender can send the data, not a problem, correct? So this link can be 100% utilized. But because of stop and wait protocol, what is happening is, if you see this one, so over the period of the time you just observe stop and wait protocol. What you do, assume that, let's say, there is no error for simplicity. If there is no error or anything, then first of all you are, and assume that, let's say, this is the transmission time, okay? Now T1, otherwise T. So then your sender sends some frame for T time, then he will wait for the acknowledgement, okay? So this is the time for acknowledgement, let's call it as some X, okay? So now after that what happens, you get the acknowledgement because there is no error in the link, definitely you get the acknowledgement. Then after that you start sending another frame, then it takes again T time. Let's assume that every frame has a fixed size. So if you don't assume this kind of things, then it will be difficult to calculate the values, right? That's why for simplicity we assume that every frame has same size. Then T and X and T and X, this kind of thing will be repeated, right, so many times. Now I can say that if I mark here to here, this is nothing for first frame, right? It is referring first frame. Here it is second frame. In that way, for every frame, if you see, so T comma X will be repeated, right? T is a transmission time. X is nothing but after transmitting the data, then remaining time to get the acknowledgement back, I can say. So now if you want to know the channel efficiency, so how much time effectively you are using your channel for only data transmission, T, right? But overall dash period of time, T plus X, it is easy to see here. In this entire period of T plus X of time, only T is useful. That's why, so I can say that the channel efficiency or utilization is only this part, T over T plus X, right? That is the formula. Now we should know what is T, how to calculate T value, how to calculate X value. Let's focus on X value. Okay. Now, first of all, what happens is, this is your frame, right? Now, what is T? Frame transmission time. So we can calculate easily frame transmission time, we have seen already, correct? So it depends on the bandwidth of the line, otherwise channel, I can say bandwidth, and second one frame size, right? Now imagine like this, there are some bits into this frame, okay? First of all, first bit immediately comes into the line, we can assume like that, correct? So it is very negligible time. So after negligible time, first frame automatically comes onto the line, then it will start running. Now the question is, at dash time the last bit will come onto the line, that is exactly equal to this overall frame transmission time. Transmitting entire frame is nothing but transmitting the first bit to last bit, right? So first bit will immediately come, maybe it takes very less time, but last bit takes exactly equal to this entire transmission time. So I can say like this, transmission time of a frame is nothing but almost the time taken to transmit the last bit, correct? That means from the duration of time from sending the first bit to last bit onto the line, correct? So now informally I can say like this, so the arrival time of the last bit will be the transmission time, correct? Now we can easily calculate, not a problem. But after that what happens, if you see, maybe the first bit is here, I don't know where it is, but if last bit is here, then it will start going, correct? So I can say like this, initially T equal to 0, otherwise time equal to 0. Let's observe the time. Let's say initially time is 0, then after T time, okay, after T time, what happened? The last bit will come onto the line, agree? Yes, that T is nothing but this one, transmission time. Now that bit will only focus on that bit now. The last bit will start going like this, How much time it will go like that? That is exactly equal to propagation delay of this line, correct? So this is propagation delay. Now after that last bill will reach here. Before that all that remaining bits already reached, correct? Now all that will be consolidated by your receiver and it will observe everything, right? Error and everything, error control, CRC, everything. So that takes some time, but in our analysis we are ignoring that part. Let's say we are not doing error or anything. So they are all negligible. Let's ignore them as 0. Now what we are going to do is, once this entire thing is over, if everything is good, we start sending acknowledgement and assume that there is no error in the line, then acknowledgement will start here and it will go like this. Okay. Now acknowledgement size is only 1 bit, let's say. Then the transmission time of acknowledgement is very less. That means this transmitter at receiver is going to transmit that acknowledgement onto the line first. After that it will start going. Assume that, let's say, transmission time of acknowledgement is 0, then what happens? Immediately that acknowledgement will jump onto the line and it will start running. Then that acknowledgement will have only propagation delay, isn't it? And because we are assuming only 1 bit for acknowledgement for simplicity, okay, then that 1 bit will exactly see only this propagation delay time, correct? Now finally if you see, what is this x? X is nothing but simply from the last bit's arrival onto the line to going to the receiver and coming back, isn't it? That is nothing but 2 into propagation delay, correct? That's why x can be replaced with 2 into propagation delay. Of course we can calculate propagation delay, not a problem, and we can calculate transmission time of a frame also. Then if you apply this formula you get channel utilization, otherwise channel efficiency. Okay, we'll see one numerical problem related to this one. Let's solve one problem related to this channel utilization of stop and wait protocol. Suppose that the stop and wait protocol is used on a link with a bit rate of 64 kilobits per second and 20 milliseconds propagation delay. Simply they have given bandwidth. So what is bandwidth? Let's call B. B is nothing but 64 kilobits. Kilobits can be written as 64 into 10 cube, right? So bits per second, right? Now propagation delay directly given, that is nothing but 20 milliseconds. We can write 20 into 10 to the power of minus 3 seconds. Now assume that the transmission time for the acknowledgement and the processing time at nodes are negligible. Yes, so even while calculating efficiency of channel we did same, right? Then minimum frame size in bytes to achieve a link utilization of at least 50%. Now we have to calculate frame size which is minimum. That means what should be the at least frame size in bytes to achieve a link utilization of at least 50%. 50% means what? With respect to fractions, 50% can be said as 1 by 2, correct? That means we should have a ratio of 1:2 or more, at least that. That means greater than or equal to 1 by 2. So this is what our target. Channel utilization should be greater than or equal to 1 by 2. So how to get it? We know the formula for that. But what is the actual channel utilization formula? T by T plus 2 into propagation delay, isn't it? Where T is transmission time. Correct. Here PD is nothing but propagation delay. So let's simplify it first of all. After that we'll substitute the values. So T by T plus 2 into PD greater than or equal to 1 by 2. If you simplify, you get like this. 2T greater than or equal to T plus 2 into propagation delay. So 2T greater than or equal to T, then T greater than or equal to 2 into propagation delay, right? So this is the formula. Now we have to substitute the values. So what is transmission time formula? Transmission time is actually nothing but message size or frame size. Let's call frame size F by bandwidth. What is bandwidth? 64 into 10 cube bits per second. Let's substitute here in the formula directly. So T equal to frame size, which is nothing but unknown. We have to calculate that F by 64 into bandwidth 10 cube bits per second. Okay, so let's keep that parameters as it is. Should be greater than or equal to 2 into propagation delay. What is propagation delay? 20 into 10 power minus 3 seconds. Now simplification, that's it. Then what should be F? F should be greater than or equal to 2 into 20 into 10 power minus 3 seconds into 64 into 10 to the power of 3 bits per second, right? So this second and second will be cancelled. 10 cube 10 power minus 3 will be cancelled. You get f should be greater than or equal to 2 into 20, 40 into 64. Otherwise 64 to the 128, 256, 2560 bits directly, correct? Because we are using bits here. Now answer should be in bytes, then f should be greater than or equal to 2560 bits by 8, then it will be bytes. So 320 bytes. So finally your frame size should be either equal to 320, otherwise greater than 320 bytes. So what is the question? Minimum size. That's why minimum size should be 320, right? So answer is 320 bytes. In that way we can answer questions related to channel efficiency of stop and wait protocol. Now we'll see one more parameter in stop and wait protocol which is easy to understand, that is throughput. So what is throughput? Generally throughput is nothing but because of your software protocols or anything, whatever it is, how much bandwidth you are able to use. Okay, that is called actually throughput. Now in stop and wait protocol, what is the maximum bandwidth you can utilize? That is also known as maximum throughput. So it is very difficult to calculate actual throughput. Why? Because in actual throughput calculation we have to see how many times we are sending the packet, because we have to consider errors also into the calculation. Whenever I consider errors in the calculation, then the problem will become very difficult. Why? I don't know how many errors I am going to get, which packet is going to get error, isn't it? Then how can you say actual throughput? It depends on the number of errors you get, right? And actual delay, how much time receiver is wasting in processing and you are sending the acknowledgements, right? If receiver uses piggyback, then it will be much more difficult, isn't it? That's why we can't calculate that kind of things. That's why we do using the mathematics only simple calculations. In our problem we are going to calculate what is the maximum throughput we can achieve. Understand? In the utilization thing also, what was the formula? T by T plus 2 into propagation delay, right? That is the maximum utilization possible in stop and wait. Similarly here, whenever I say throughput, sometimes I say throughput, but here our intention is what is the maximum throughput we can achieve. So let's try to have maximum throughput. For that, no errors should be there. Second one, no processing time, nothing. Only thing is, so we are transmitting the data, that will go and acknowledgement will come back, and transmission time of acknowledgement let's take negligible. But if you really want to consider that time also, then that's a separate issue. You know the logic, right? If transmission time is also should be included in for acknowledgement, let's do that also, not a problem. But in my problem I am teaching such a way that acknowledgements are completely negligible. That means we are not calculating the transmission time of that. Okay, but it's not a big deal to include that. Okay, now no errors. Then what is going to happen? We know that. Let's just summarize. So we are sending the frame, and after that we are waiting for 2 into propagation delay for acknowledgement, correct? You know the utilization formula. What is that? T by T plus 2 into propagation delay. I can say that over this period of time, T plus 2 into propagation delay, you use this T time, right? That means I can say, to calculate the throughput, what I can do is, so this part I can use. Finally, in this entire time, T plus 2 into PD time, that means frame transmission time plus 2 into propagation delay, in this entire overall period, you were able to send only one frame, isn't it? I can say like this. Finally, answer is one frame per this entire period of time. What is that period of time? First send the frame, that last bit will reach after T point of time, that means transmission time. Then the last bit will go here. When last bit goes here, now acknowledgement starts coming. Then this entire thing is 2 into propagation delay, and the last bit will come to the line after transmission time. So total T plus 2 into PD, in this overall period of time, only one frame. This is a maximum throughput possible, right? Let's try to solve a numerical problem related to this one so that you can understand. From now onwards, simple. Maximum throughput of stop and wait protocol is simply one frame per this overall period of time. Okay, T plus 2 into propagation delay. Now we'll see one more question. A channel has a bit rate of 4 kbps and propagation delay of 20 millisecond. Fine. frame size used is 1 kb. If the protocol used is stop and wait, then what is the maximum throughput which can be achieved? We know how to calculate, right? We'll do it. So we know that in stop and wait protocol, we can send one frame over the period of dash time. That is nothing but throughput, right? So one frame over the period of one frame transmission time, let's say t plus 2 into propagation delay. That's it. For that we have to calculate transmission time and propagation delay. So what is the transmission time of the frame? Simple. Transmission time formula is frame size 1 kilobytes. Let's convert it into bits. So 1k, that means 10 cube, into byte means 8 bits, correct? Message size by bandwidth. What is the bandwidth? 4 kb. 4 into k means 10 cube. BPS means bits per second. So now if you write clearly like this, it will be easy for you to simplify the thing. Sometimes what happens mistakenly, if you don't convert bytes to bits, then here what happens? So at the top nominator will become bytes and in the denominator you get bits, then you don't get the correct answer. So all the measurements or whatever it is, they should be uniform. They should be in a same way, right? If you take here bits, everywhere you take bits. If in some place you take seconds, everywhere you take seconds. That would be the good idea. 10 cube will be cancelled, then 4 to the 8. So here that second, if it goes top, then it will become seconds, 2 seconds, right? So finally transmission time is 2 seconds, correct? Now what is the frame size? One frame equal to 1 kb. So 1 kb by, so t is nothing but just now I got 2 seconds plus, here we have to simplify 2 into propagation delay. 2 into propagation delay is nothing but 20 millisecond. Let's convert it into seconds. It will become 40 millisecond, right? 40 millisecond is nothing but 40 into 10 power minus 3 seconds. It would become, so 10 power minus 3 I can cancel with 0, then still 2 more zeros, then 0.04. So you get here 0.04. I can say that 1 kilobyte per 2.04 seconds. So if I convert it into bits, it will become 10 cube into byte means 8 bits per 2.04 seconds. So you have to do the simplification. If you do the simplification, you get some answer. So this is the throughput of stop and wait protocol. That's it.